Hey, my name is Anton, and I'm happy to be able to have this presentation at this workshop. My colleagues and I have won the Gaze Prediction Challenge, and in this presentation I'll describe our solution and our ideas. Above all, we are independent researchers. We don't have experience with eye tracking, and it was our first time in this area. I'm working at I2X in Berlin as a backend engineer. Svetoslav works as ML engineer and he is from Voronezh, and Vladimir from Moscow and works as senior CV engineer at Cifra. Actually, we were doing a competition in our free time. A few months before the competition, we've started to research a topic of modeling human visual attention. We've begun our research related to datasets, papers and supplement materials. Our initial point was a database of eye movements called Hollywood video clips. Soon we've discovered OpenEDS competition and decided to participate. Let's talk about task. The task can be formulated as follows. Given 50 gaze vectors, we had to predict 5 gaze vectors in the future. In the out-of-sample subset, history of that 50 vectors was absent, so we needed to predict them too. On the right side of the slide, you can see metrics for this competition. Our main idea was to split solution in two parts, the estimator and the forecaster. We wanted to avoid sequence-to-sequence solution because for us it was too hard and we thought we don't have enough time to implement it. The estimator takes one picture and predicts vector for it, and forecaster takes 50 gaze vectors and predicts the following 5. So our whole pipeline take a sequence, predict all vectors for the sequence frame by frame, predict the following 5 vectors. Let's talk about the estimator. Here our main idea was to use augmentations. Augmentations are widely used in order to extend dataset and make model prone to errors. Mostly used as color augmentations, as geometry augmentations. We didn't find any existing solutions for gaze vectors, but found for B boxes, for key points and for our labels. And we decided to write our own solution. We took augmentations library and made a path for it. So our forks is capable to augmentate gaze vectors. You can see original frame, also augmented vertical flip, and shift, scale and rotate augmentation. Let's talk about models we used. We've tested the following models: ResNet 18, ResNet 34, MobileNet version 2, EfficientNets different versions. And we choose ResNet 18 for our final solution. Which insights do we have? Extensive augmentations increases the score, and training works fine with careful learning rate schedule. The estimator have achieved very low error between ground truth and predicted vector. And because of the test subset, I will talk about it on the next slide. Carefully trained estimator was the key to win, on our opinion. So what's wrong with test set? We've predicted all test sequences by the good estimator and tried to explore the end of each sequence. We've made some visualizations and checked the amount of movements in the last 10 frames for every sequence. There are only 500-600 sequences with non-static movements in the whole test subset, which contains 6,400 sequences. And we've decided to improve our estimator and keep the forecast simple. On the right side, you can see visualization of gradients between 2 frames for all test sequences. We have a few thoughts about data and about the metric. Looks like we need to resplit our dataset because forecast over static sequences doesn't contain a lot of meaning, so far as we know. If we will add more sequence with any movements in the end of it, it will be more helpful to predict them, but not static sequences. And also our second thought about the metric. Why metric error is equal for the first and for the fifth frames of all predicted frames? it's harder to predict fifth frame than first, so maybe we have to do something here too. So what do we know now? We know that we don't need complex models for the forecaster, but in the beginning of this competition we wanted to implement this paper about eye movement prediction with Kalman filter. And also we know that improving of the estimator gives more than improving the forecaster because of test subset. And reducing error of the estimator is better for static sequences than reducing error of a forecaster. What did we try to do with the forecaster? We tried to use different methods for the forecasting, like exponential smoothing, linear regression for each sequence, rolling average, ARIMA models, recurrent nets, and other methods. In the same, we tried to make our sequence more smoothly because we predict frames, not all sequence, and juggling was a problem for us. Good point here was Savitsky-Golay filter. Visually it works fine, as you can see on the chart, but on the validation it decreased its score a bit. So in our final version we don't use it, but we think it can be very useful in the real life. And on the chart you can see the estimator, the original track, and Savitsky-Golay filter for each excess for specific sequence. So our final, the forecaster solution is very simple. Check if there is movement at the end of the sequence. We calculated average gradient of the last 7 frames. If yes, we just add this gradient to the last prediction 5 times for each prediction frames. And if no, we just apply rolling average on the last 3 frames and we add new frame to the end of sequence and then recalculate average of the last 3 frames and make it 5 times. We make it for different axes separately, but we think the best decision here is to use LSTM networks. We tried one, but it was learned on the bad predictions because we used test prediction from the estimator for training our LSTM network and we didn't have enough time to retrain it. Also, it isn't so useful for the static sequences. And thank you for the competition and for your attention. I'm ready to answer any questions. Thank you again.